now. Next one. All right, so the oxyanion of nitrogen, which has the highest oxidation state, is the nitrate ion, so NO3 minus. And the corresponding oxyanion of phosphorus is PO43 minus. So PO43 minus is stable, and NO3 minus is stable. So as you can see, phosphorus has 4 oxygens around it, while here nitrogen only has 3. So the other thing is that NO4 3 minus is not stable, and PO3 minus is also not stable. And so we want to compare the bonding structure to look at why this would be the case. Okay. So for NO3, so first of all, let's look at NO3 minus. So we have 5 valence electrons here. We have 6 valence electrons times 3, which is 18. So that's 18 plus 5 is 24, but we can't forget the negative sign. 18 plus 5 is 23, but we can't forget the negative sign, so we get 24 valence. So you got N, O, O, O. Just putting in the typical valence here. And adding one more for fun, apparently. Yep, I just keep doing it. Okay. And then we do need to add in one more for the negative, so I'll just put it there. And it looks okay, except we've got unfilled valence for these guys. So then we might as well give one of the electrons to an oxygen to get an octet on 2 of the oxygens and a double bond to the other. And so now octet is satisfied everywhere. We've got a delta negative here, a delta negative here, and a delta positive. So the total charge will be negative, but the total charge will be -1, and our octet rule is satisfied everywhere. Okay. So then, and the other thing to point out here, especially for this question, is that our nitrogen is sp2 hybridized. And this double bond is being formed from the overlap of a 2p orbital with a 2p orbital. Or actually, just to emphasize this a bit more, this double bond is being formed from a nitrogen 2p orbital overlapping with an oxygen 2p orbital. Okay? And so already we can see why PO43 minus might be tricky. So PO3 minus, sorry. PO3 minus would be phosphorus, oxygen. So just drawing the same structure again. This, delta minus, delta positive. Trying to draw the same structure, but failing. Okay, and so this double bond here would actually be a phosphorus 3p orbital overlapping with an oxygen 3p orbital. 2p orbital, sorry. And so because, just because that's where we have our electron density in phosphorus. So we're going to have significantly less overlap between a 3p and a 2p than we would a 2p and a 2p. And so this is going to significantly weaken this bond to the point where this is actually quite reactive. Alternatively, we could draw this, especially because phosphorus can become hypervalent, as this structure. Where phosphorus now has 5 bonds, but that's okay. Phosphorus can deal with that. But then, of course, this would be a P3P overlapping with an oxygen 2P and a 3D overlapping with an oxygen 2P, which might be a little better, but still not perfect. Although the negative charge is now firmly on the oxygen. But either way, we do have this higher N overlap going on. Okay. And then, so now looking at PO4 3-. So in this case, we've got our phosphorus, our oxygens are going to surround it. Okay, and our phosphorus, I'm going to give 4 electrons. So how many do we need here? So we've got 5 valence, 6 times 4 equals 24. So that's 24 plus 5 is 29, and then it needs a 3 negative charge, so that's 32 total. I'm going to go ahead and give these guys their doubles. And I am missing 1 from phosphorus, so I'm going to give it to this guy here as well. And so that could be one potential structure, where here we've got a delta minus on each of the oxygens and a delta positive on the phosphorus. Okay. Or alternatively, we could pull that in and give us a structure like this, which is now resonance stabilized, because our phosphorus can become hypervalent. And so we've got 4 oxygen atoms surrounding it. We've got quite a bit of charge delocalization across the structure. But alternatively, we can split this around here like this, as phosphorus can become hypervalent, so it doesn't mind having 5 bonds. And although we have quite a bit of charge, there are also significant resonance structures here, right? So each of these can go up and down, leading to many resonance structures stabilizing the charge delocalization. Okay. And and this double bond, even though this double bond would be fairly weak, as it's going to be a phosphorus 3D with an oxygen 2p, we've got lots of space to do this, and the charge delocalization will help to stabilize the structure. So for NO4 3- though, we're kind of stuck with this structure, as nitrogen doesn't really have access to the d orbitals. And so then we're stuck with this structure, which is heavily charge delocalized. So whether we've got a positive charge on the nitrogen and negative charges on each of the oxygens. So this structure is going to be not very stable and want to separate, especially with all this negative charge around the periphery. So all these oxygens are going to want to split, and we can't do this. We can't do this trick where we force nitrogen to become hypervalent, as we don't have access to those d orbitals, and so we won't have this charge delocalization, which you would see for PO4 3-. Okay, so just to sum up, NO3- is a stable structure in which we get, and I didn't mention this before, but this also gives us resonance structures, right? So each of these could become a double bond. So our NO3- can lead to charge delocalization, which gives us some stability as well. Our double bonds are overlaps between 2p orbitals on nitrogen and oxygen, which will give us favorable overlap. For PO3-, looking at the same structure, we would still end up with some stabilization due to resonance. But we would actually only get very minor delocalization across these two oxygens, across all three oxygens actually. But our double bonds are all going to be formed from N=3 orbital overlaps, with N=2 overlaps on the oxygen. So these are going to be much more significant, much weaker orbital overlaps, giving us much weaker double bonds and leading to a structure which falls apart much more readily, or is much more reactive. In the case of PO4 3-, the ability to become hypervalent allows for, even though the double bond might be weak, it does allow for heavy delocalization of charge across the structure. And although our 3D to 2p overlap isn't great, it's still better than nothing in this case. And NO4 3-, we can't access this hypervalent property for nitrogen, and so we've just got massive charge aggregation of the oxygens, which would cause quite a bit of repulsion and cause the molecule to fall apart. Okay. So now if we look at the solution, so the nitrogen is not large enough to accommodate all 4 oxygen atoms, so that's essentially what we are saying here. So in PO4 3-, we can form favorable overlap between 4 oxygen atoms, or there is a way to do it. And allows for some stability. An NO3 minus, so both of them have p orbitals of similar size, so both of them are 2p's. Well, in PO3 minus, it's a larger p orbital or a 3p orbital, so it's less effective. So I'd say solution is correct, although a little incomplete.